My name is Sidney. I actually just finished just defended my master's 2 weeks ago, so I'm free and done. But I'm still working in lab a little bit, trying to tie some loose ends. Oh, sorry, just not spoiler. Okay, so I'm going to start, talk a little bit about me. I'm from Calgary. I was born and raised in Calgary, which makes me a Flames fan. I don't think they game tonight. And this is from last game, and this is usually a sad picture because the Sidney just scored. There's actually me right there, but I'm pretty disappointed. But luckily this lady's covering my face. Okay. So after high school in Calgary, I kind of wanted to move out and kind of be independent and an individual. So I decided to come to UC and study biochemistry. And while I was an undergrad, I had to summarize or give one experience I think was the most important thing in my undergrad was science co-op, so to do co-op. Because the co-op program let me work at Amgen, which is an international multi-billion-dollar pharmaceutical company. I got to work with a lot of expensive machinery and learn a lot of cool stuff. Got to work on projects that develop new pharmaceutical products and medicines, like one of these products by Amgen is Prolia, which is a treatment for osteoporosis. And my second work training co-op, I got to work here in my Smith laboratories with Phil here, my supervisor, and all these lovely and smart people. Okay, so I'm going to talk about concepts that are important for the heater lab and lab that I worked in, and for my project. First, I'll start with model organisms. Anyone know what a model organism is? Or any idea, any guesses? Yeah?
Organisms that can be used for scientific things.
Yeah, that's essentially it. So they're non-human species used to study biology or disease. So what are some useful traits for model organisms? Yeah.
Something like similar immune systems to humans.
Yeah, so similar to humans is a good thing, yeah. Anything else? Anyone know any? Well, we'll go through that. So, yeah.
White rats.
Okay, white rat's example of one, rats, yeah. So why don't we have gorillas as model organisms? Okay, yeah, okay. So they're also not very small, so the gorillas are big and they can probably beat you up. So useful traits from model organisms, they're small and easily manageable. You can stick them in the fridge, things like that. They quickly reduce, as I said. So you can create you can do many experiments within your own lifetime, not the way a human lifetime to do an experiment. They're usually genetically manipulated, and this is not really a useful trait, but it's good to consider ethics in that gorillas are kind of hard to work with because they're very similar to humans, they have feelings, they feel pain, and you don't really want to experiment on gorillas because it's kind of sad and kind of. Okay, so we're just going to run through some model organisms so you guys learn about some model organisms. Anyone know what this is? Yeah, E. coli.
E. coli is a model organism?
Yeah. It's probably the most widely used organism in all science.
First I heard it was a disease, then I heard it was in our intestinal tract.
Yes.
Now it's a model organism?
Yeah, so E. coli, as I said, is just a bacteria essentially. And it's in our gut, so we actually have trillions of bacteria cells in your intestine. It's also related to E. coli poisoning or disease, but that's because you ingest E. coli from a cow or from another human or a non-human source. So you find E. coli in your food essentially. So, anyone know what this is?
Yeast.
Yeah, what's it?
Yeast.
Yeah, yeast. Okay. Everyone know what yeast is? What do we use yeast for bread? Bread, beer, wine, fermenting. So yeast is another model organism. Anyone know what this is? I think the leaders are probably seeing these from my last slide, but you guys should shout it out. What is this?
Flagellum?
Yeah, flagellum is like a tail or something, but it doesn't have
Seminal.
Anyway, it's a roundworm.
Just
It's a
kidding.
nematode. Or a C. elegans. And you find these normally in the dirt and in the soil, but they're a multicellular organism about 1,000 cells long or big. And everyone knows what this is? Yes. Fruit fly. Anyone know what this is? Other than a fish.
A fish.
Okay, deep fish, yeah. And this everyone knows is mouse. Okay, so there are more model organisms, but to me these are the main ones and probably the most widely used ones. And the way I ordered them is because the top row, they're single-celled organisms, obviously, they're just one cell big. The second layer, they're multicellular, they have many cells, they have segmented bodies, they have differentiated tissues. And then lastly, the vertebrates, so these are the most closely related to humans. So all these we can use to study essentially biology, anything biology related, and especially disease research. Okay. So another thing I want to talk about cell lines, which Laura mentioned briefly, and this isn't, they're not technically organisms, so I didn't include them in the previous slide, but they're also important in research and in my own thesis. So cell lines are essentially, they're cells that come from a human or mammalian source, and they've been taken away from the organism itself and grown in a culture, in a tissue culture, and so it's growing its own media, and it behaves as if it's its own organism, but it's not an organism. Obviously, it's just the cells that have been taken away from the organism. So these are actually, this is an image of one of the most widely used cells, the HeLa cells. They're called HeLa cells because they came from this lady named Henrietta Lacks, who was born in the 1920s, and she unfortunately died in the 1950s. She died of ovarian cancer. So these cells are actually cancer cells from her ovaries. And she has a very interesting story. If you're interested, there's a pretty good book out here, The Moral Life of Henrietta Lacks. It's very easy to read. You don't even know any science background, but it's interesting to hear about the background of these cells. I put these up here because it's pretty interesting that these cells, even though she died over 60 years ago, like I have cells in the incubator that are from her, and there's probably trillions of her cells throughout the world. So she'll probably, like, if you put all the cells together, she'd be like the hugest human ever. Okay, so I'm going to talk about my thesis, which is essentially cancer, or cancer research. So what's cancer? Everyone knows what cancer is, but how would you describe what cancer is? Yeah.
Cancer is a bunch of cells continually growing and metastatizing throughout the body and causing harm.
Okay, perfect. If I had to just give it in 3 words, it would be uncontrolled growth and metastasis. So your cells are growing uncontrollably, and this is going to cause metastasis and spreading of those cells, which is bad. So this uncontrolled growth is really due to genetic mutations, though. So their ability to divide inevitably or infinitively is due to genetic mutation. So what I studied in the lab and in the Peter lab specifically studies is a phenomenon known as genome instability. So genome instability is just like the state that cancer cells are in which it's very easy to accumulate mutations. So anyone know what this is a picture of? Chromosomes. Okay, so on the left here, we have a nice healthy chromosome from a nice healthy cell. Everything is in 2 copies, everything's diploid because we're human. And over here we have a karyotype from a cancer cell. And so what's different about this versus here is that you can see how there's more than 2 copies in some of the chromosomes and some of the chromosomes. I think they only have 1. Actually, no. They either have 2 or more than 2, which is not what you want. And in addition to that, you can see here how the ends of these are different color than the main body of the chromosome, which means that this chunk of the chromosome got chopped off from some of the place and got transplanted there. So everything's really messed up. This is genome instability. Okay, so in the HeLa lab and in my thesis, we tried to find determinants of genome instability. So what's actually causing this, because this actually contributes to the uncontrolled growth that we see in cancer. Okay, so I think I want to get a little more technical, but I think it's a good idea for you guys. So there's 2 main types of genetic mutations that you might have heard about. Essentially, a loss of function mutation, which means you don't have enough of the gene product, or a gain of function mutation, which means you have too much of the gene product. So I was interested in gain of function mutations, which lead to genome instability, because loss of function mutations have more traditionally and classically been characterized before. So this is more of a newer thing that we can study. So this is my research question. Can too much gene product essentially cause genome instability? Okay, so this is actually from my thesis, some data. Essentially, what I found was that too much of this protein in yeast, called MPH1, resulted in increased mutation. So here on the y-axis, I have essentially mutation rate on the y-axis, and on the x-axis, I have different genes that I overexpress. And you can see here, MPH1, when I overexpressed MPH1, so I made the cell express MPH1 protein too much, it resulted in an over 200-fold decrease versus just normal cell. So these cells that are that have too much NPH1 protein are mutating very, very quickly. And what this actually looks like on a plate is, so this plate has media on it that will select for mutants, and on the left you have a wild type normal cell. You can see how there's maybe 1 or 2 cells per each spot. So these cells here mean that these cells have, or these colonies here mean that these cells have acquired a mutation. And here I have cells or strains that are overexpressing NPH1. You can see how there's many, many more cells that have acquired mutation. Okay, so in yeast, this gene is called NPH1. In humans, it's called FANK-M. And FANK-M is interesting because mutations in FANK-M genes, or FANK-M, can lead to Fanconi anemia. And Fanconi anemia in humans is a disease, and it's bad, but essentially you have developmental defects. So here you have some dysmorphism in the face, you have developmental problems in your hands, in your chromosomes. There's a lot of genome instability going on. So what you see here is essentially these chromosomes are pairing or coming together incorrectly. And what this means is that you get stem cell failure and 1,000-fold increase in risk of cancer, especially blood cancers.
1,000-fold?
Yeah. So if you have Fanconi anemia, if you have this genetic mutation, you are essentially guaranteed to develop blood cancer or leukemia within your lifetime. And the median age of survival is only 30 years old for people. Okay. So any questions? I thought it was pretty cool because essentially I found a gene that makes mutation, that increases mutation in yeast, and even though I use yeast, no one really cares about yeast, no one really cares about curing diseases in yeast, but we can use that data to really apply it to humans and cancer disease. Questions? About anything? Really made sense?
You get